Hi everyone. Today I want to solve this FE exam heat transfer problem for you. We're going to make sure that we solve this problem step by step and really focus in on the fundamental of this problem, which is closely related to the idea of external flow. External flow is coupled with the idea of convection, which is subsection B here under the subject heat transfer. And this is the FE mechanical specification I'm showing here. Let's read the problem and understand what they're asking for, and then we'll come back and compile our inputs. So water is flowing over the upper surface of a flat plate here. We're given some dimensions of a flat plate. It says the flat plate surface temperature here. We're given at the film temperature some properties of the flow. We're given the Prandtl number here, which is a combination of different properties, and it's a dimensionless term. The thermal conductivity, as well as the kinematic viscosity, and we're looking for the heat transfer rate, and BTU per hour is what is specified in. You can see that this problem is in English units here, and I'm sure some people cringed at the fact that this is in English units, but the FE exam tests both English and metric units, so it's a good idea to get some practice with both of them. Let's compile some of these inputs here. By the way, you can try this problem for yourself using the first link in the description below, and you can do that before watching this video solution. Let's compile these inputs. So we have the temperature of the water is equal to 68 degrees Fahrenheit. We have the flow speed is 5 inches per second. It's flowing over the upper surface of a flat plate. We're given the length of that flat plate is 2 feet. And we're given the width. It has unit width into the page. That's 1 foot. The plate surface, the temperature of the plate is 104 degrees Fahrenheit. And at the film temperature, we're given a Prandtl number equal to 5.43. A thermal conductivity K equal to 0.355. BTU per hour, what's degree Fahrenheit, and a kinematic viscosity, that's equal to the dynamic viscosity divided by the density. That's equal to 8.6 times 10 to the minus 6 foot square per second. And our goal is to find the heat transfer rate. That's a Q dot term. And we know that we have a fluid kind of flowing over a surface. Whenever you have fluid flowing over a surface, that is convection, right? Fluid movement that transfers heat is convection. We know that the most important equation that we have when dealing with convection is the fact that the heat transfer rate is equal to HA Ts minus T infinity. That's Newton's law of cooling, where H is the convection coefficient, A is the area that the heat transfer is occurring, Ts is the surface temperature, and T infinity is the temperature of the flow. Okay, so the things that we know here are area. We also know what the surface temperature is and T infinity. We're looking for Q dot, and we also don't know the heat transfer coefficient. So external flow is all about finding that heat transfer coefficient, and we can do that by looking in the FE reference manual here. We check in the reference manual under the section external flow, which is on page 210 of the reference. What you can find is some equations here based on the Reynolds number. The Reynolds number based on the length of the plate. We can compute that and see if it's greater or less than 10 to the fifth, which is 100,000. If it's less than 10 to the fifth, we can compute another dimensionless term called the Nusselt number. And the Nusselt number can be computed using the Reynolds number and the Prandtl number. And then we can use that to get our convection coefficient. Knowing the convection coefficient, we can plug back into Newton's law of cooling and then find our heat transfer rate. So that's our idea. Let's go ahead and write down exactly what the Reynolds number is, compute it. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam. as well as a detailed solution manual for each exam so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top three subjects, what are my bottom three subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software FE Interactive will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $9.99. Let's get back into the video. The Reynolds number at the end of the plate is equal to the speed that the flow is traveling at. That's what I called U multiplied by the length of the plate. That's 2 feet here divided by the kinematic viscosity we can put. Technically, this term is mu over rho. So that's pretty much what we substituted in over here. The speed is equal to 5 inches per second of the flow. The length of the plate is 2 feet, and the new value is 8.6 times 10 to the minus 6. If we look at the units here, we have foot square per second in the denominator. We have a foot and then an inch in the numerator. So we need to convert that inch to feet. What we can do is in 12 inches, there's a foot. So we go ahead and convert that. If we go ahead and calculate what this is, 5 times 2 is 10 over 12 divided by 8.6 times 10 to the minus 6. We get a value here equal to 96,899.22. We can take this Reynolds number and plug it into that Nusselt's relation that we had. So let's go ahead and do that. The Nusselt number based on the length is equal to 0.664 times the Reynolds number based on the length raised to the 1/2, Prandtl number raised to the 1/3. We have all the information that we need to plug into this equation here. Reynolds number 96,899 that we just found. I'm going to take the square root of that, and the Prandtl number was given as 5.43. Go ahead and do this calculation. Square root of the Reynolds number times 5.43 raised to the 1/3 power. What we have is 363, and the Nusselt number is dimensionless here. So we have what that's equal to, and we know that it's also equal to h bar, the average convection coefficient, times the length over k. So all we need to do is multiply the 363 value we have, multiply by k over L, and then we can find our average convection coefficient. Then we can plug into Newton's law of cooling. We have a k value of 363. K value is 0.355. The length of the plate was 2 feet times 0.355 over 2. We get 64.48. That's BTUs per hour foot squared F. Let's go ahead now and plug into Newton's law of cooling to find that Q dot is equal to 64.48 times the area. It's 2 by 1 or 2 square feet. TS, the surface temperature of the plate, was equal to 104 degrees. That's this right here. Minus the flow temperature, T infinity, that's 68 F. Our Q dot is equal to 46.42. That's BTUs per hour. Let's go ahead and check this answer. That's pretty close to this answer up here, choice A. Now, if you don't have time to watch the full solution here, what you can do is, using the first link in the description below, you can access this interactive problem and view the solution. And if you're struggling, you can definitely watch the video solution here. That's linked back to this video right here. If you enjoyed the video, consider leaving a like and subscribing. Thank you for watching. I'll see you in the next video. Goodbye.